Welcome to the Explainer. Today we're diving into one of the most mind-bending mathematical puzzles and, honestly, one of the most fascinating historical artifacts of the 20th century. We are exploring a machine built to be completely flawless, a device whose very name is practically synonymous with secrecy, the Enigma Cipher. But before we start tearing this machine apart, I want you to chew on a seemingly impossible contradiction. How in the world did a machine boasting 158 quintillion possible settings, a level of perfect, unassailable mathematics, ultimately become the absolute greatest vulnerability for the German armed forces during World War II? It is an incredible story of absolute mechanical perfection clashing with deeply flawed human habits. Okay, let's dive into this. Here is our roadmap for today. 1. The ultimate secret weapon. 2. Inside the cipher machine. 3. The plugboard's massive math. 4. 100 quintillion keys. 5. Symmetric encryption explained. And finally 6. Finding the weakness. All right, part 1. The ultimate secret weapon. History of the Enigma. To really understand why this thing was built, we have to look back at the absolute security disasters on both sides during the First World War. I mean, traditional pencil and paper techniques, they were failing miserably. Military commanders desperately needed a much higher level of secrecy and far more advanced methods for encrypting their messages. The solution actually kicked off in 1915 when 2 Dutch naval officers invented a machine to encrypt messages. Fast forward a bit to 1918, and a German businessman named Arthur Scherbius patents the Enigma and starts selling it commercially to banks and businesses. But the real game changer arrived in 1926 when the German armed forces adopted a specially adapted military version. From that point all the way through World War II, they relied heavily on it, totally convinced that their communications were completely unbreakable. Now, just looking at this sturdy mechanical box with its standard keyboard, you wouldn't immediately realize it's hiding an immense compounding mathematical puzzle. Honestly, it kind of looks like an overgrown typewriter. But beneath that metal casing is a literal engine of pure cryptographic chaos. Which brings us to part 2, inside the cipher machine, scrambling the alphabet. Let's crack this thing open and see how it actually scrambled letters piece by piece, starting with those core internal mechanisms. The basic operation was a 3-step journey. First, the operator types a plaintext letter on the keyboard. Second, an electric current zips through these different scrambling elements, specifically a series of rotors. Third, the resulting enciphered ciphertext letter lights up on the lamp board right above the keys. But here is the absolutely crucial part. Every single time a key was pressed, the movable parts inside the machine physically changed position. So, if you hit the letter A, it might light up as Q. But if you hit A again immediately after, it might light up as F. This constant mechanical shifting completely obliterated the traditional frequency analysis methods that codebreakers used to crack simpler codes. And the complexity just skyrockets when we look at the rotors themselves. The Army issue Enigma actually came with 5 different rotors, and the operator had to choose 3 of them to slot into the machine. Those rotors moved a bit like a car's odometer, but instead of 10 steps, they took 26 steps for each letter of the alphabet. Plus, the operator had to set the exact starting position for each of these 3 rotors, meaning any one of 26 letters could be the start point. Oh, and there were also internal metal rings on these rotors that could be adjusted, throwing yet another layer of mechanical complexity into the mix. So let's look at part 3, the plugboard's massive math, amplifying the complexity. Because those spinning rotors, that was just the warm-up. The real mathematical explosion happened right on the front panel of the machine at the plugboard. Before the electric current from a typed letter even reached the rotors we just talked about, it passed through here. Operators used physical cables to plug pairs of letters together. If A was plugged into B, typing A instantly diverted the current down the path normally meant for B. It intercepted and swapped the letters right at the source. And the Germans didn't just use 1 or 2 cables. They used exactly 10 cables to swap 10 pairs of letters out of the 26 available. When you apply combinatorics to this, choosing 10 pairs from 26 objects, the math goes entirely vertical. This single step creates exactly 150,738,274,937,250 possible setups. That is roughly 150 trillion variations, just from the cables on the front of the machine. All right, part 4, 100 quintillion keys, the unbreakable equation. Let's pull all of these components together and calculate the final, honestly terrifying scale of the Enigma cipher. First up, we have the internal rotors.
When you calculate these 60 different ways to position the 3 rotors chosen from a set of 5, and multiply that by these 17,576 different starting positions, you get just over 1 million possible setups. So before we even touch a single cable on the front, we already have over 1 million possibilities.
Next, we take that million and multiply it by that massive variable we just learned about, the roughly 150 trillion combinations created by the 10 plugboard cables. And here is the grand total, 1.58 times 10 to the power of 20. That is 158 quintillion possible ways to set up this machine. Just let that number sink in for a second. If you were a German commander looking at this math, you would be absolutely certain your communications were invincible. Attempting to guess the exact daily setting out of billions and billions of potential keys, it was mathematically impossible. Moving to part 5, symmetric encryption explained, communicating in secret. Now, you might be wondering, how do you actually communicate with something this insanely complex? If the machine generates 158 quintillion variables, how does the person on the other end read the message? Well, it operates on a principle known as symmetric encryption. In this system, the deciphering process is actually incredibly simple, provided you have one specific piece of information. The algorithm is the machine itself. But the key to unlocking the message is the exact setup. The decoding key is exactly the same as the encoding key. So a German soldier receiving a scrambled message simply typed the ciphertext into his own Enigma machine. If his machine was set up perfectly identically to the sender's machine, the original plaintext letters would instantly light up on the lamp board. And this brilliantly illustrates the fatal flaw in the entire system. The machine's math was theoretically unbreakable, but because it relied on symmetric encryption, every single operator in the field needed to know the key. So the German command issued physical, monthly key sheets, telling operators exactly how to reset their machines at midnight every single night. The Allies knew the Germans were using Enigma. The security didn't rest on the math anymore. It rested entirely on keeping a physical piece of paper out of enemy hands. These key sheets were guarded fiercely. They were even printed in soluble ink, so they could just be washed away with water if capture was imminent. Which brings us to our final part, number 6. Finding the weakness, cracking the system. So the battle lines were drawn, right? Mathematical perfection versus the desperate need for intelligence. We are left with a burning question. If you cannot realistically calculate 158 quintillion possibilities, and you can't capture the key sheets, how do you break the unbreakable code? Well, this was the monumental task facing the brilliant code breakers at Bletchley Park. Their greatest tool wasn't brute force at all. It was actually something called a crib. A crib is essentially making a highly educated, correct guess for a small, specific part of an encrypted message. If you could guess a tiny fragment of the original text, usually you needed about 12 or more letters for it to be effective, you could instantly bypass millions of useless machine settings and isolate that daily key. Now, the German operators were trained to prevent exactly this. They stripped out all the spaces between words so codebreakers couldn't spot the length of common words, and they transmitted messages in uniform blocks of 5 letters. But they were human, and humans are creatures of habit. Operators would send routine messages at the exact same time every day using the exact same phrasing. Stuff like send help or weather reports starting with consistent wording. These entirely predictable human habits provided Bletchley Park with the exact 12-letter cribs they needed to isolate the daily key, crack the cipher, and read the messages. In the end, the Allies did not defeat the 158 quintillion mathematical possibilities. That math was, and honestly still is, impenetrable. Instead, they defeated the flawed, predictable human system operating the machine. It really forces us to ask ourselves, even as we build infinitely complex security technologies today, are our systems truly secure, or are we simply overlooking the human element that operates them? Thanks so much for joining me on this explainer. Until next time.